So this would be the last lecture for constructions. Um, from next week, we're going to start a new topic. Announcement. No class on Thursdays, December 12th. Now let's continue from last time about complex Bolovac-Erdős graph. I will give you the general definition of the construction, and then we start talking about the properties of this construction. So complex Bolovac-Erdős graph. In the most general setting, our goal is to construct a dense graph that has bounded clique number and has sublinear generalized independence number. Right. So let's fix two integers. So set up fix integers P and Q. Integers. And then we're going to set rho to be the qth root, primitive root of unity, equals to cosine 2 pi over q plus I times sine 2 pi over q. So you can also write it as 2 pi I over q. This is the primitive qth root of unity. Okay. Then we're gonna take some further constants. Take constants from right to left. Let me write it like this. So this means given Q, we're going to take K sufficiently large so that this holds. And given K, we're going to take epsilon sufficiently small so this holds. And then we're going to take, on top of this, some dimension, H. And H is a large number to be determined later. This is the dimension of the complex sphere. This will be the dimension of the complex sphere that we would take. Okay, we're going to set further that this parameter mu to be epsilon over square root 2h. And we're going to take n to be sufficiently large. So we've mentioned this lemma. When n is sufficiently large, in terms of mu, we can cut the surface, the complex sphere, into equal measure pieces. Let's normalize the measure to 1 so that each piece, equal measure, each piece has diameter mu. Right. So by the previous lemma, the first thing we do is to cut the h dimension complex sphere into n over 2 pieces set let's call it d1 to dn over 2 of equal measure. Of equal measure, since we normalize the whole sphere to have measure 1, so equal measure means measure 2 over n and rate and diameter strictly less than, let's say, mu over 4. Okay. So this is we're beginning the construction now. Let's cut the sphere into small pieces. Now you arbitrarily pick a point from each region, each one of these sets D. Call this choice the capital set X, and you pick another copy of arbitrary points, one from each region, y1 to yn over 2, call this set Y. We will construct the almost bipartite graph between X and Y. So pick xi, yi arbitrarily. In di, then you let X to be this set. Now we're going to construct our set G. Is our complex Bolobash-Erdős graph. G have vertex set V, edge set E, where V consists of X union Y. So let's see how we define edges. We've mentioned the case where P equals to 1, Q equals to 3 last time. So the general case is similar. Maybe I should write it all in one page. Right. So for the inner edges, as I mentioned, I think I draw some picture last time here. For inner edges, that means inside X and Y, okay? We have X is X1 to Xn over 2, Y is Y1 to Yn over 2. Between Xi, Xj found an edge. If and only if, let me write it down, there exists some rotation, which is a power of the primitive root, rho, such that 1 is roughly at this rotation. If you rotate xi by this angle, you get xj. If and only if such that xi minus rho k of xj is small. So in terms of picture, this is the picture. Okay. I don't need y. Y is the same. Just delete this. This is the picture when q equals to 3. Okay. Example where q equals to 3. So xi is adjacent to a small neighborhood at the if q equal to 3, rho is just rho q equal to 1, right? It's the cubic root. That means rotating by 120 degree. So rotating by 120 degree, and you can perturb a little bit some small neighborhood. This is neighborhood of that. Or squared of that, when q equals 3, you either multiply by rho or rho squared. That means rotate one more time, perturb a little bit, small neighborhood there. Okay. One thing I need to mention is that this constraint is symmetric for index I and j. It's not directed graph. Okay. Here, this is symmetric. In I and j. Because this condition is the same as xi minus rho kxj equals to, you just multiply the other side by this. This is the same thing. Okay. That's the inner edges. Now the cross edges between x and y. Same thing as the cubic case. Let me first copy the picture. Okay. For the cross edges, xi adjacent to yj, if and only if it satisfies two conditions. A, for any, we need to scoop out some strip around the equator or some rotation of the equator. So for any k in Q, we require the imaginary part of this number, which is the kth power rotation of the inner product between xi and yj. Is to be at least k times mu. Okay. Second condition is that their inner product of xi and yj lies in it's in the unit disk by Cauchy-Schwarz and lies in the unit disk the first p over q proportion of the pie chart. So they're writing it mathematically, there exists some alpha, which is the angle between 0 and 2 pi p over q, such that e of negative pi alpha, this is rotating. If you look at the inner product and rotating clockwise by alpha angle, you fall onto the real line. So here's a picture. So in this picture, P, in this example, P equals to 1, Q equals to 3. Okay, and how do we read this? the strip that will scoop is this one. And is it this color? Right. And B correspond to this color. So, okay. This is the strip excluded in A. Okay, once again, if you forget about, just take K to be 0. Take K to be 0, this is just 1, yeah? Rho to be 0 is 1. This is saying, first of all, by Cauchy-Schwarz, what is Xi, Yj? They live on the complex unit sphere. So they have norm 1. So inner product of two norm 1 vector by Cauchy-Schwarz has norm at most 1. So Cauchy-Schwarz implies Xi, Yj has norm at most 1. It lives in the complex unit disk. This is the disk I'm drawing here. Now, think of K equal to 0, no rotation. Inside the unit disk, it should be above. This is the imaginary SX, right? It cannot be too close to the real line. Imaginary part cannot be too small. So this is excluding this part. And the other strip is just you rotate this by some power of the primitive root, right? So again, similarly, you cannot be too close to this axis, the rotation of the x-axis. This is another rotation of x-axis. We will see why this is useful. Scooping out something here, and we will see that this part that we scoop out has measure. This has measure little o1. So it's not affecting much of our density. Now, part B, this part is where the inner product should lie, right? The inner product lies somewhere inside this unit disk. After alpha clockwise rotation by P over Q angle, so when P and Q is 1/3, it just means that it lives in the first 1/3, right? After some rotation, it gets on here. This is it. This is the permissible region in B, which we will see that it has measured roughly P over Q minus little o1. Okay. That's the construction. Any question? Now we need to prove some properties of this construction. All right. Properties of these. So just for you to remember, let me put this thing here again. How inner edges and outer cross edges are determined. The properties of the complex polar Bachelor-Radix graph. The first property we will prove is that So this is like a Q through root rotation, right? For the inner edges. So intuitively, when Q equal to 3, this is Q equal to 3, P equals to 1. When Q equal to 3, you have lots of these triangles. That's how you made them adjacent, right? But it's impossible to have K4. How can you have K4? Well, Xi needs to be, neighborhood needs to jump here. Then the next neighbors need to jump here. Then this form a triangle. What does the fourth one go? The fourth one then has to go somewhere again here. Then these two are too close. So it's KQ plus 1 free. That's the first thing we're going to prove. Intuitively, that's true. Um, so the time. So here's the first fact. 1. This fact is a pure computation. Okay, let me sketch the proof. For any inner edge, if xi, xj form an inner edge, is an edge, then their distance cannot be too close. Okay, 3 over q. If they form an edge, they cannot be too close. And later we will show that if you have a k4, kq plus 1, then two of them must be very close to one of these corner. But then they contradict to this fact. Okay, so how do we prove this? Suppose xi actually form an edge, that means by definition there exists some k such that xi minus xj times rho k. They are very close. One is close to a rotation of another, right? Certain rotation by definition. Now use triangle inequality. Let's look at their difference. It's bigger than triangle inequality xj minus rho k xj minus xi minus rho k xj. Okay, this is the common term, triangle inequality. Now this is small because of this, and this one you can extract xj. Xj is unit vector, so it's basically 1 minus rho to the k. So this is strictly bigger than 1 minus rho to the k minus the small error term, square root mu. And then there's some calculation. This one can compute that is bigger than 3 over q. I will skip the calculation. All right. Calculation is not so interesting. Now let's use this to prove inside x and inside y, we induce a kq plus 1 free graph. Claim 2. X and y each induces kq plus 1 free graph. Proof. As I said, suppose there's a kq plus 1, suppose there's k4. By definition, every 2 must be a certain power rotation of another. Then by pigeonhole, if there's 4, 2 of them must be very close, contradicting to this fact 1. Okay? So suppose we have x I 1, xi 2 to xi. Okay, why? By rewriting the indices, let's just suppose x1 to xq plus 1 induces a clique or contradiction. Okay, then what do we know? we know for each then we know by definition for each R in Q, we have there exists KR in Q minus 1, just by definition of the inner edges, such that XR minus rho KR's rotation X 1 okay, messed up with the indices. Maybe let me start with X0, X1. This is a KQ plus 1, say. Okay, and this I put 0. I just shift the index by 1. No big deal. Okay, so we know that each XR must be a rotation of X0 by some power of rho. Okay, up to error term. Now, how many? We have R of these other guys apart from X0. We have Q of them, but the rotation option is only Q minus 1. So there exists two vertices here whose rotation is the same. They rotate the same way. So that there exists two, they both rotate as square. They both are here. So this pigeonhole implies there exists R not equal to R prime in Q such that KR equals to KR prime. That's what it means, right? Now let's look at their distance. Look at the distance of these two, XR minus XR prime. And they are forming an edge, right? These two are adjacent. But their distance, we're going to show that they are too close, contradicting to this. This is at most, again, triangle inequality. It's XR minus rho KR of X0 plus rho KR prime, which is the same as rho KR, X0 minus XR prime. So it's less than 2 square root mu, which is a contradiction when mu is sufficiently small. So 2 square root mu will be smaller than this. Each x and y induce a kq plus 1 free graph. If you take q equals to 2, it's the same as the original Bolubash-Erdős graph. Each part is triangle free. Okay. Next property. Next property is it has sublinear generalized independence number. So for this, next we want to show this. For this, we need some tools. The next thing we will show is using, let me see, upper lower bound. It's probably lower bound on the cap measure. Give me a second. we need, okay, for now, let me just say, we just use some sort of isodiametric inequality. Do we need concentration? Okay, let me write it like this. So we will use some bipartite version. Isodiametric inequality to show that alpha of G, this the P generalized independence number is sublinear. It's little o n. This just means for every set of size omega n, GU contains a copy of KP. Okay, this is what we want to prove. Sublinear independence number. Let me first state this bipartite version of isodiametric inequality. Lemma 3. So for mu, given mu between 0 and 1, and given two sets A and B, which are subset of the complex sphere, H dimension, with measure, this is normalized Lebesgue measure, not too small, positive measure, okay, 2 times e to the negative h nu. Then we can find what it roughly says that if you take any two sets, subset of the complex sphere, when they have positive measure, then you can find 2 points, one from each set. They are almost antipodal from each other. So then there exists A in A, B in B, such that they are almost antipodal. Okay. Meaning, given two sets of positive measure, there exists a pair of almost antipodal points, one from each set. This is what it means. Let's take this for granted. And what we're going to prove is this corollary. Again, we have nu between 0 and 1. We're given a set A of positive measure. With measure lambda of A is bigger than 2 times Q times e to the negative h nu over 16. Still a positive measure. Q is fixed constant. Then we can find Q points in A. They sort of evenly space out at this Q corner of this regular Q-gon, say. Then there exist points A0, A1, to AQ minus 1 in A, such that they are evenly spaced out, meaning rho K, AK, you can reorder them. So rho K, AK minus is very close to rho L, AL. Okay? For n in K and L. If you take Q equal to 3, this just means we can find 3 points whenever A has positive measure, we can find 3 points. They are roughly is evenly spaced out at this 120 angle. Okay. Any questions about the statement? We can think of this as a complex version of this well-known fact that in high-dimensional sphere, whenever you take a subset of positive measure, then it contains 2 points that are almost antipodal. But now antipodal is like north and south, right? We are in a complex setting, so we introduce rotation. It's at this equal angle rotation. Now, how do we prove this? The proof is simple. We basically show that we scoop out bad sets and let's see the proof. Let's define a bad set for each rotation, k, in q minus 1. Define, let this bad set bk to be those points in A such that there's no A prime in A with A plus rho k A prime bigger than 2 minus nu over 16. Okay, this just means, what does this mean? This just means these two, for A, there's no other A prime such that after rho k rotation, A prime gets to a very close vicinity of A. If it gets here, then the sum, they almost line up. The sum of these two goes here. The norm is 2, right? The length is 2. Okay. This is the bad event. Okay. And why is this bad? Well, look, the good event is we want to find the set A such that in any rotation of rho, power of rho, there is something here at this region. Then this will be, you take one from each region, you'll be the Q tuple that we need. So this is saying that those points A, where after rotating rho kth power, there's nothing here. No A prime in this region, in A. Okay. Now we first show that BK has small measure. This is corollary of this isodiametric, the bipartite version. The reason being, we know A has large measure. If BK also has large measure, we satisfy the hypothesis, right? Then there exist 2 points lining up. A and negative B, they line up. So you just apply, let me write it. First note that if the measure of BK is also large, then by the lemma 3, BK apply to BK and not A, but rotation of A by minus rho k, apply to these two sets. What do we get? We will get 2 points A and B. So A coming from BK, B coming from here, such that A minus these, which is this guy, is at least 2 minus mu over 16. We take mu to be mu over 16 here. That contradicts to the definition of BK, okay? Contradicting and predicting the definition of BK. So that means, so this means measure of union of BK K in Q minus 1 is at most is less than equal to 2Q minus 1 e to the negative h nu over 16, which is less than the measure of A. Okay, that means there are some points in A that does not lie in any of this BK. And you can pick an arbitrary point there, and this point there means in every rotation, there's some guy here, okay? You can just pick the guy. So this implies A minus BK is non-empty. Okay, then just take a arbitrary A0 in this set. And you take their corresponding points. Okay. And take their corresponding point. The remaining is calculation. I will not show the calculation, not so interesting. Okay. All right. Now, this then implies, what does this imply? Now let me confuse points with vertices, because each vertex lies in the region of small measure, a small diameter. So this diameter is an error term. So let me just think of points as vertices. Now, this is basically saying whenever you take a positive measure correspond to a linear number of vertices, omega n of vertices. Whenever you take omega n of vertices, you will find q vertices that at the equal angle at this nice position. That means they form a clique of order q. And that's exactly what we want to prove. Of order q. So here I should write q. Sorry, I made a mistake here. Okay. When any linear size set, you induce a KQ. This is the corollary. Let me directly write the corollary. Corollary 5 is that alpha gx, the Q's independence number, is at most 2Q e to the negative h mu over 20 times x. Okay, so we just need h nu goes to infinity, then this guy goes to 0. So it's a little o of n. So we will need here, remark, we need h goes to infinity so that, well, actually we just need h times nu goes to infinity. Okay. So e negative h nu goes to 0. Okay, from this proof, actually, it's not hard to extract that for every KQ, if you have a copy of KQ in X or Y, they are all spaced out in this nice position. Okay, from the same proof, so we know that for any KQ, we can enumerate its vertices in X. We can order its vertices as V0, V1 to VQ minus 1, such that they space out nicely, such that rho K VK minus rho L VL is less than square root nu for all KL. So we prove that both X and Y, they are KQ plus 1 free, and their alpha Q independence number is sublinear. Next, we want to prove that we want to bound this clique number of the whole graph. That's the final thing, and the edge density. Oh, sorry. Okay, let's first do the edge density. The edge density. The edge density is pure computation, actually. So I will skip this part. Intuitively, let's look at this picture. You have inner edges, which here you have little o n square edges. The inner edges is not hard to show. For the cross edges, even though for a pair of vertices, they are adjacent, even though we scoop out some small strip, as I said, this small strip has measured little o1, it can be shown. And their inner product lies in this whole unit disk. The probability, since points are uniformly distributed, vertices, the probability that lies in here, as you may imagine, is the relative measure of this with respect to the whole disk, which is P over Q. So 2 points xi and yj form an edge. When we uniformly random pick these 2 points, it's probably P over Q, and that gives the edge density. I will not do this part of the calculation. It's standard calculation. So Gx, as I said, Gx, Gy has little o n square edges. And between X and Y, edge density P over Q minus little o1. So this part I skip, but believable. The most important thing is to bound the clique number. Okay. So let me give you some idea of where we at for this knowledge. So for this graph, what we know now is we're going to prove in our results. What's known is when P, remember we picked this P and Q. If P is less than equal to Q over 2, then we have the graph G is K P plus Q plus 1 free. But we cannot go beyond this. So it's still open when P is strictly bigger than Q over 2. This sort of construction. The smallest open case is this Ramsey-Turan density. Ramsey-Turan density, oh, let me just directly write it. When P equals to 2, Q equals to 3. This corresponds to K6 free and alpha 3 of G is little o(n). Okay, the smallest open case. Now let me give you a proof of this for the baby case when P equals to 1, Q equals to 3. Baby case, P equals to 1, Q equals to 3. This we can do. We can prove that this is P5 free. We will show proof. In this case, G is K5 free, which then implies the Ramsey-Turan density, the generalized Ramsey-Turan density for K5 is 1/6. Okay, provides this lower bound 1/6, and we have the upper bound also 1/6. So equality holds. Right. Suppose there's a K5. If there's a K5, okay, how can the K5 appear? We have X, we have Y. Because we know X and Y, suppose there's a K5. X and Y are both KQ plus 1 free, remember? And Q is 3, so it's K4 free. Each one of them is K4 free. So this copy of K5 must have 3 vertices on one side and 2 vertices on the other side. So suppose this K5 has vertices, say A, B, C in X and U, V in Y, let's say. Okay, so it looks like this. We have the cross edges. This is the only possibility to have K5 up to symmetry of X and Y. Now, let's first write down what this adjacency means. First of all, the inner adjacency, ABC from a triangle, means they are at this 3 corner of a triangle, right? They are one a primitive cubic root rotation of another. So the edges, inner edges, means, first of all, A minus B times rho is the cubic root, and A times C times the square rotation of rho is small. And also U and V, UV, also satisfy this. It's less than square root mu. Okay, this is what we know. Where rho 1 plus rho square equal to 0. Rho is the cubic root of unity. Okay, let me now write this. Now, first thing to notice is that when ABC, they sitting, we know whenever you have a triangle, it must sit nicely at the 3 corners. Then if you sum them up, they are balanced. You sum them up, it's very close to the origin. They have small norm. So the sum of the 3, ABC, has small norm. That's easy to prove. This implies A plus B plus C equals to, this is B minus A row square plus C minus A row. Okay, why is this true? This is because row is the cubic root, so it satisfies this, meaning that A equals to negative A rows minus A row square. Okay. Now we can split, use triangle inequality. This is at most. Hmm? I pair up in the wrong way, right? I can let me pair up this way. Okay, so it's not correct either. Wait. Okay, so this is less than row square. This is fine. B row minus A. Okay. Plus row C row square minus A. Now it's correct. This is norm 1, so you can get rid of it. And what's the norm of these two? They are tiny, so this is less than 2 square root nu. Good. Second of all, this guy has small norm, and we know this guy also has small norm. So the product of these two, Cauchy-Schwarz, has small norm. Now, Cauchy-Schwarz implies that A, B, C, let's take their arithmetic mean times the inner, this means inner product. This means inner product. Okay, I'm lazy to write this one times U minus V row is less than mu. Oh yes, less than 2/3 mu, right? Because this guy is less than this guy is less than that, time these two together, no problem. We will get a contradiction to this inequality. So this is our Hart inequality. The inner product of these two complex numbers is very close to the origin, has small norm, okay? Now, how do we bound this from above? Let's see where they lies on this unit disk. First of all, so far we've only used inner edges to derive this. Now let's use cross edges. Cross edges are these 6 edges from the ABC side to UV side. We have edges there, that means blue edges, that means the inner product of any left-right pair must lie on the first 1/3 of this pie chart, right? So now let's use cross edges. We have 6 of them. 6 cross edges. From ABC implies that the inner product of AU, BU, CU, AV, BV, CV all lie in this region. All lie in this region. Remember, we scoop out a tiny bit. We scoop out some strip. Remember, this strip is roughly k mu width that we scoop out, and the remaining part is where it lives in. Let me just write like this. All lives in here, in this region. In particular, this region is a convex region. Okay, convex region means any convex combination of these are 6 points in the unit disk lying in this convex region. Any convex combination of these points still lies in this region, right? So in particular, convexity this is where we use P is at most Q over 2. Because when P is at most Q over 2, this blue region is convex. If P is bigger than Q over 2, it will correspond to some region that's not convex. Then convexity cannot be used. Okay, so convexity implies, first of all, A plus B plus C. This is just nothing but the convex combination of these 3 points, right? So this another convex combination of these 3 points, they all lie in this blue region. Also there in this region. Okay, but the point we cared about is negative this guy times negative this is inner product, yeah? So the inner product we cared about is this guy times negative rho rotation of nu. What is that? This multiplied by okay, conjugate. So let's look at where does this guy lies in. A plus B plus C over 3, comma, negative rho times V, right? I think this equals to the conjugate of this guy. You can pull it out. Conjugate this is negative rho square, right? Probably negative rho square A plus B plus C over 3 V. Okay, and where is this guy? Well, this is this. Multiplied by -1 is counterclockwise 180 degree, right? So this is counterclockwise 180 degree. Counterclockwise. And this is counterclockwise. One row is 120, so it's 240 degree. Together is what? So together is counterclockwise 60 degree. So that means this guy lives in here. Let me use a sharper color. Oops. lies in purple region. 90 degree. 60 degree. So it lives here. Lives here. So altogether, this guy sum up with the other guy, which is this guy, lies in the union of these two, which is this upper half disk with this strip scoop it out. So what do we know about this upper half strip disk? It has imaginary part at least k mu. So it doesn't satisfy this. This has imaginary part is at most 2/3 times mu. Just take k to be strictly bigger than 2/3, we get a contradiction. All right. So this implies A plus B plus C over 3, the inner product with U minus rho V, this inner product. The norm is at least, by our definition, we scoop out this strip, so it's at least K mu. But this is at most Cauchy-Schwarz. We know this is at most 2/3, less than 2/3. Do I put? I'm not sure if I should put this. Less or less equal. Doesn't matter. Contradiction. Okay. Any question? Once again, let me summarize. Why is K5 free? Each part is K4 free. So K5 can only have 3 vertices on one side and 2 vertices on the other side. The inner edges implies that this ABC and UV, they should be at some rotation, 120, multiple of 120 degree rotation from each other. And this triangle must be nicely spaced out. That means the sum of ABC has small norm. So Cauchy-Schwarz, small norm times small norm, you have small norm. Now let's see what this guy lies in on the unit disk. Let's split out this inner product with these two terms. By the cross edges, A inner product with U, or B inner product with U, or C inner product with U, all lies in this first 1/3 pie chart. So if you take the convex combination, still lives in here. Same with V. But now we have this minus rho vector, which is the same as rotating counterclockwise 60 degree. But 60 degrees is fine. That means all this thing, they still live in this upper unit disk with a strip of width k mu scoop it out, exclude it. That will imply that the norm of this is at least k mu. That's a contradiction to them having a small norm. Okay. Any question? So now I have a reading assignment for the person taking this note. Let me briefly sketch one more construction. Also a nice recent development on lower bound on multicolor Ramsey number. So let me define this multicolor RT. Let's say you have L colors. is the minimum n such that for any L edge coloring of Kn, we will get a monochromatic KT. Monochromatic KT. So the standard diagonal Ramsey is just this, in this notation, two-color Ramsey number. Okay. For two-color Ramsey number, we know now RT2 recent breakthrough says is less than 3.9 to the T. Okay, and is bigger than basically square root 2 to the T. 2 to the T over 2. Square root 2 to the T. This is no. For a while, so there's no improvement over this, exponential improvement. And for a while, the three-color one, there's no improvement over this trivial bound square root 3 to the T until this recent work by Conlon and Ferber, who improved this three-color and all larger number of colors. So for three-color, let me write it. Now for three-color, the best is, maybe let me just directly write it. Now, multicolor, we have for every fixed R, T, L color is at least 2 to the 3 over 8 L minus 1/4 T minus a lower order term. Okay. If you take L to be 2, you get 2 to the T over 2. It's the same as this one. Okay. So when L equals 2, it covers root 2 to the T. L equal to 3. This was first proved by Conlon and Ferber. And L equal to 4 and above, this bound is the construction I'm going to tell you by Yuval Wickerson. I think there is now even improvement by solving. You should check later, further improvement. Check the literature. But let's today see this construction. This is what we'll see, which recover also all these cases. This construction is easy to describe. Let's first define a very special graph. This also is an illustration of combining randomness plus some algebraic construction. So you don't do completely random. You do some structural thing and then you do something random. Whereas here, I think he just replaced this algebraic initial construction by a pure random one. Okay, so what is this algebraic construction to start with? Let's define this graph G0. So initial algebraic graph. Let's call it G0. The vertex sets V is a, a subset of length t binary vectors with even number of ones. Okay. Hamming weight just means the number of ones it contains. So with even number of ones, then easy to see that half of them are even, half of them are odd. So it's 2 to the t minus 1 weight. Okay. How do we define adjacency? We have two vertices or two vectors in U. If and only if their inner product is non-zero, forming an edge. If and if only if their inner product is 1. That's the adjacency. And this inner product just the usual one that's defined over F2. Okay. The first thing to notice is that this graph, initial graph, has no large clique. It has no clique of order T, lemma, G0 has no clique of order T. It's like an odd town, even town. So V consists of vector length T vectors of even weight. So then it's not hard to see that if you form a clique, then these corresponding vectors of these endpoints of the clique must be linearly independent. But since V has dimension T plus 1 in this space, linearly independent means there are at most T minus 1 linear independent vectors. That's it. Okay. It just means proof vertices of a clique in G0 corresponds to linear set of linearly independent vectors. And the dimension of V is T minus 1. That's it. Okay. There's another one, lemma. I will not prove it, but for you to read, is this graph. Independent set of size T, there are not so many of them. So G0 has at most 2 to the 5t squared over 8 plus little o t squared. Independent set of size at most t. Okay. I'll skip the proof. So the initial structure, very easily simple algebraic graph. Vertices are length t binary vectors with even having weight. Adjacency if they are not orthogonal, so their inner product is 1. This graph has small clique number, and even though it has a large independence number, but large independence set, there are not so many of them. Small clique number, few large independent sets. We're gonna now take random blow up of this algebraic graph G0, and then we take copies of blow up of G0 and randomly overlap them together. That will consist of the first L minus 2 colors. For the remaining 2 colors, whatever pair of vertices that are not covered by any one of these blow up of G0, we're going to color them the last two colors uniformly random. So let me write it down. Coloring. So we're going to take n to be 2 to the 3 over 8 L minus 2 t plus t over 2 minus little ot. So this will be our capital N. Now we're going to take consider blow up, n vertex blow up of G0. Let G1, G2, GL minus 2 be blow ups be how do I say? Random blow up. M vertex random blow up of G0. Okay, this just means you blow up each vertex equally, and then eventually, well, almost equally. Eventually, you have M vertices, capital M vertices. This will be one blow up. Now you can just randomly permute its vertex sets. You obtain a copy of this GI. You take the union of these L minus 2 copy, put them together. This is the ideas we've seen it in previously, the alone Rödel idea we mentioned when we talk about this multicolor K4 versus clique. Remember? Put them together. So we will get a new graph. And this graph, you color the edges by whichever copy it comes from. If it comes from multiple copies, that's fine. Just call it by an arbitrary color. Let's say E belongs to G2 or GL minus 2, you just color it, let's say G2, color by the minimum one. Okay. Be random blow up with G0 and color edges of Kn by which copy of G0 it comes from. Which copy of blow up of G0. Okay. But there's some edges are not covered for any edge not in union of GI. Color it with color L minus 1 and L. Uniformly at random. This is the random bits. Okay. Now here we've described a coloring of Kn. First of all, if this edge is coming from one of these random copy blow up, you color it by that copy. If not, we have two colors left. If it's not covered by any, you call it uniform random, the remaining two colors. Okay. Then I'm running out of time. Then just by a standard first moment calculation, we can show that with positive probability, easy first moment union bound. So we can show that with positive probability, this coloring does not contain any monochromatic KT. First of all, no monochromatic KT in the first L-2 colors is trivial because each one of these GI does not contain a clique of order T. These are blow up of G0, and G0 does not have this large clique. So does its blow ups. So do its blow ups, right? Now, we just need to be careful with the complements of these unions. And the complement of this union, first of all, not many independent set of, it must be an independent set in all these colors to live in the complements. Since there are not so many independent set of size T in each copy, so not so many independent sets of size T survive in the complement 2 color at the first place. Then then you have to multiply by another 2 to the T choose 2 minus. This is the probability that it all gets all these T choose 2 pairs of vertices in these T independent sets gets color L-1 or L. Okay, a simple calculation. I will not do this calculation. Any question about the construction? So this is another recent construction illustrating a combination of something structural, like this from algebraic construction, together with some randomness. The last 2 colors are random. Okay. We can get some improvement over some pure random construction. This will conclude the constructions I want to talk about. As I said, next week, there's no more class this week. And from next week, we will start a new topic. Okay. If there's no question, we're going to end it here. See you guys next week.